Over the past year or so, we've had a few SPH SIG events, and the discussion around the future of the method has often felt quite interesting, and it's touched on high order and the challenges that poses, but there's never particularly seemed like we've had enough time to really go into it in any deeper. So I thought it would be a good time to share some of the work I've been doing over the past 2 years on a new method called LABFM, which to some extent bridges a gap between SPH and high order finite differences. So I'll provide a little motivation and then give sort of the detail of LABFM, or the local anisotropic basis function method. Then I'll spend some time going through some various aspects of the method, so accuracy, consistency, stability, and show some example implementations to highlight its current and potential capabilities. Then I'll end with a little discussion on the challenges that I think high order mesh-free methods might pose. And I was going to say I'll try and leave a little bit of time for discussion about this, but as it's a webinar, the discussion will have to be through the Q&A. So I've shown this slide before as motivation for high order mesh-free methods. So I mean, for any given method, there are a number of characteristics, accuracy, efficiency, flexibility, which are desirable. And obviously, each method has its strengths and weaknesses. So SPH in its traditional form has excellent conservation properties and geometric flexibility when we think of simulations of breaking waves and things. And it's pretty easy to implement. However, the areas that it's sort of let down in are accuracy or consistency. So this is an example illustration of the convergence properties of some typical methods. So we've got resolution along the bottom and that error up the side. So with methods like finite differences, finite volume, finite elements, we typically see convergence around second order. Then we've got high order finite difference methods where we might get convergence 4th, 6th, 8th, 10th order. Then spectral methods where we get exponential convergence. But with SPH, there's typically a range of resolutions where we can see convergence typically between first and second order. And then after that, depending on the circumstances, we generally get some kind of plateau where we reach what's often called the discretization error limit. I mean, high order methods are desirable. Firstly, we want a consistent method because we want to know that as we throw more resources at a problem, we're going to get a more accurate answer. But if we have a high order method, then we can get either a more accurate answer for a given cost, or we can get the same accuracy of answer for a reduced cost. And I've been guilty of creating convergence plots like this myself. So I think I probably presented this one at a spheric talk a few years ago. And I've taken a few points over a really small range of resolutions, less than an order of magnitude. I've drawn a nice straight line through some of them, and I've just declared that the convergence rate is 1.3. But what I've completely ignored is the fact that if I kept on converging, my results would get worse. And whilst SPH with convergent characteristics like this still has a raft of uses, in many applications, it becomes a bit hard to demonstrate that we're competitive with mesh-based methods when these are the convergence plots that we can produce. So this really motivated us to think about how we can develop sort of formally high order mesh-based methods that exhibit convergence characteristics more like high order finite differences. So I've included this slide called "What is SPH?" because I think the answer depends on your perspective, and I think my perspective is a little different to the traditional SPH perspective. So traditionally, we think of SPH as a discrete system of Lagrangian particles, each with a fixed mass. And really the density summation becomes sort of the key equation. So from this equation, everything else follows. And we get this Hamiltonian system where the symmetries in the system mirror the symmetries in reality. And then we get exact conservation of linear and angular momentum and mass and energy. Now, I've spent quite a bit of time working with incompressible SPH, and I think this has a slightly different perspective. We tend in incompressible SPH to start with the Navier-Stokes equations, and instead of building the method from the density summation, we tend to construct our numerical scheme around the Navier-Stokes equations using discrete SPH gradient and Laplacian operators as building blocks. And we sacrifice global conservation for local accuracy. So in an incompressible SPH perspective, this equation, some sort of SPH gradient or derivative operator is sort of the central element of the method. And so really from this perspective, SPH is just a way of approximating spatial derivatives of some data on scattered nodes or particles. So this work really focuses on mesh-free methods from this perspective, based on a sort of generalized form of this type of operator. But we aim to construct it so that we get the desired level of accuracy or convergence. So before I move on to the actual method, I'll just briefly run through some of the notation that I'm going to use. So firstly, everything I show here is going to be in an Eulerian scheme with fixed particles or nodes, unless I specifically say otherwise. M represents the order of consistency of the method. So that is the maximum order of a polynomial for which the method is exact, which means our gradient operators should converge with resolution to the power of m, and our Laplacians with resolution to the power of m-1. The stencils, they look just like SPH stencils. And I'll denote the characteristic node or particle spacing as S, and the characteristic length scale of the stencil as H, which is akin to a smoothing length. And it's worth noting that node volumes and masses don't really enter into the formulation at all, because this is really based on polynomial interpolation of the data within this stencil. So I'll first define this general local discrete operator L on this stencil, which is the sum of the differences between the properties of the node I and its neighbors, multiplied by an ij specific weight. So L approximates a specific partial derivative, and this vector of partial derivatives here and a kind of flag vector are simply a notation we've introduced to identify which derivative we're trying to approximate. So for example, if we're trying to approximate d by dx, then we set the first element of CD equal to 1, in which case this term is equal to d by dx. So we're saying that we're approximating d by dx. Another way of looking at it is that the vector CD contains the desired moments of these weights, wji. So the moments being the x, y, x squared, xy, y squared, etc. For example, if we want to approximate a Laplacian in an ideal world, we'd have the x squared and the y squared moments equal to 1 and all others equal to 0. So I refer to this as a general discrete operator because it can represent a range of methods. So it has the same form as the antisymmetric SPH gradient operator that I've been using in incompressible smooth particle hydrodynamics. And in that case, the weights wji are just equal to the kernel gradient multiplied by a particle volume. It could also represent a finite difference operator, in which case the weights wji would be linked to the indices of the ordered nodes divided by a measure of the node spacing. And this is the operator that we're going to base LABFM around. So how do we get a consistent, how do we make that general discrete operator consistent? So first, we decide that we're going to construct our ij specific weights from a series of anisotropic basis functions, so it's W1, W2, W3. They're anisotropic in as much as they depend not only on the magnitude of the interparticle vector, like an SPH kernel does, but they also depend on the direction of this vector. The vector psi is just a series of coefficients, or a vector of coefficients, and psi is the vector that we need to find, basically. So I won't go into the derivation here, but the process of constructing the operators is really as follows. So for every node, we construct a local matrix where we introduce the vector of Taylor monomials x, and for each node we build this matrix, which is the sum over the neighbors of the tensor product of the monomials x and the basis functions w. So the resulting matrix, essentially, each column of that matrix contains the moments of a given one of these basis functions. If we then write this linear system, any psi which satisfies this linear system will result in the operator L having polynomial consistency of the order determined by how many elements of these vectors we've used. So we solve this linear system, and then we use the psi that we get to calculate the weights. So if we've set m equals to 6, then in 2D we'll have matrices that are 27 by 27. We solve those, and then we'll find that the operator L has consistency of order 6. So it's exact for all polynomials up to 6th order. And that's equivalent to saying that that the gradient operators will converge at 6th order and the Laplacians at 5th order. So that's the first part of the method. But the key thing really then is, how do we choose our anisotropic basis functions? So I've explored two approaches. The first is to set the anisotropic basis functions as a series of the partial derivatives of a radial basis function, and that radial basis function could be an SPH kernel, for instance. If we do use an SPH kernel, then this has the nice benefit that in the low order limit of m equals 1, so when we just have a 2 by 2 system for that consistency matrix M, then we recover the Bonnet and Locke SPH gradient operators, so first order consistent. An alternative approach is to set the basis functions as the product of a radial basis function, which again could be an SPH kernel, multiplied by some orthogonal polynomials. So Hermite polynomials, Legendre or Laguerre polynomials all work similarly well. Now these figures in the top and the bottom, they show the logarithm of the absolute value of some of these basis functions. And we can begin to see what the purpose of these basis functions is. So the basis functions split the stencil into regions. The higher the order of the basis functions, the more divisions there are. They're effectively sampling the node distribution within the stencil. The type based on a radial basis function split the stencil into segments, whereas the type based on orthogonal polynomials split the stencil into squares, or in 3D cuboids. The conditioning of the matrices that we have to solve, these linear systems to get the corrections, is dependent on how well these anisotropic basis functions sample the discrete stencil. And what we found is that the orthogonal polynomials give rise to much better conditioned matrices, and they become less sensitive on the node distribution or changes to the node distribution. So it's actually quite simple, really. That, in a nutshell, is the local anisotropic basis function method. We build consistency correction matrices using some choice of anisotropic basis function. We solve them, and then we store some weights, which we use in a sort of finite difference style discrete operators for our gradients or Laplacians. So I'll now move on to some numerical results. So first we look at convergence when approximating the derivatives of a function. So for our test function, we look at a sort of pseudo-random 16th order polynomial over a unit square on a node distribution, which is disordered and fairly typical of what we'd get in an SPH simulation. These shifts that I've applied to the polynomial are the sort of random part, just to ensure that there's no symmetries cancelling out any errors. It's basically to make it a slightly harder challenge for the method. So the figure on the left shows the convergence rate of the gradient as we increase the node spacing, and on the right we see the convergence rates for the Laplacians as we reduce the node spacing. So for the gradients for orders m equals 2, 4, 6, 8, and 10, we get convergence rates of 2, 4, 6, 8, and 10. And for Laplacians, we get convergence rates of 1, 3, 5, 7, and 9. And I think it's worth noting these blue lines at the top are the results that we'd get with an SPH operator, just as standard SPH operators that I've been commonly using in my incompressible SPH code. And you can see that we're getting, I've written a fair bit more accurate, but really quite a huge improvement in accuracy. So in some quite believable circumstances, say at this kind of resolution, we're getting 6, 7, 8 orders of magnitude better accuracy. There's still a limiting error for these operators. So for finite difference operators, we'd expect convergence rates to continue all the way down to a machine precision error limit. In SPH, the convergence rate is limited by the discretization error, which is basically the error due to us not accounting for the particle distribution. In LABFM, we're accounting for the particle distribution up to a certain order. So we get this convergence rate, but when we account for the particle distribution, we have to solve these linear systems. And as we go to higher orders, the linear systems get bigger and the residuals from solving them get bigger. So at really high orders, say 10th order, then the residuals start to increase and become significant at very fine resolution. So we get these limiting error levels, but they're still an awful lot lower than or an awful lot more accurate than we could get with something like standard SPH. So now I'll have a look at the effect of changing the stencil size with LABFM. So the color of these plots shows the error with resolution along the bottom and the stencil size up the side. So as we move left on one plot, we're going to a finer resolution. As we move up, we're going to a bigger stencil size relative to the node spacing. So we see, it's just off the bottom of this plot, but we see for each value of m, so for each order that we're looking at, there's a clear limit above which, so for larger stencils, the method converges uniformly. And for smaller stencils, the method diverges or certainly doesn't do very well. And this limit is, as I sort of alluded to before, this limit is imposed by the requirement that the anisotropic basis functions adequately sample the node distribution within the stencil. And if we've got higher orders, then we have more complex structures in our anisotropic basis functions. So we need more nodes in the stencil in order to adequately sample these basis functions. It's worth noting that this requirement of stencil size isn't actually that difficult to satisfy. So for fourth order, we can get away with stencil sizes of about 20 in 2D or 80 in 3D, which is pretty similar to what we'd use in smooth particle hydrodynamics with something like a Wendland kernel. For sixth order, we go up to needing maybe 50 or 60 nodes in the stencil in 2D. And if we were to go to 8th or 10th or 12th order, then we'd end up needing sort of 100 odd nodes in the stencil. The next aspect of the method I wanted to look at is the resilience to the node disorder. So the plots are similar to the ones on the previous slide, but here as we move upwards, we're going from a uniform distribution of nodes to a severely disordered distribution of nodes. And again, we see that these vertical contours indicate that the convergence rate is pretty uniform up to really quite high levels of node disorder. So for fourth order, we can get up to almost node disorder of the same order as the node spacing. For sixth order or eighth order, that drops a bit, but ultimately a node disorder of 0.5 corresponds to a distribution which looks a bit like this, which is worse or sort of more disordered than we're likely to get in an SPH type simulation. So it looks good. It looks like we can have simulations where the accuracy remains high even when we have quite severely disordered node or particle distributions. So I'll now move on to some actual fluid dynamics simulations. So I've implemented LABFM to solve the isothermal compressible Navier-Stokes equations. And in most of the simulations I show, the spatial discretization is sixth order. Time integration is with a third order Runge-Kutta scheme. The code's written in Fortran and parallelized with MPI plus OpenMP. And we employ a sort of high order filtering or de-aliasing technique to stabilize it. Now, there's really no two ways about it. High order co-located methods require some kind of stabilization. In spectral methods, they use a de-aliasing by just eliminating the top third of the spectrum. In finite differences, they often use filters. So we construct a LABFM based high order filter where the coefficients are set in some pre-processing step so that they satisfy some de-aliasing rule. And we use this to stabilize the simulation. So it's very, very closely comparable with the approach that's used in high order finite differences. By way of a brief validation, on the right, there are two figures. I'm just going to close the window because it's raining heavily. On the right, there are two figures showing the error when simulating Taylor-Green vortices. So there's an analytic solution for Taylor-Green vortices in the incompressible limit, but our simulations are isothermally compressible. So in the top, I'm using sixth order LABFM, and I'm reducing the compressibility. And I see that as I reduce the compressibility, we keep between fifth and sixth order convergence, but we lower this compressibility related error limit. On the bottom, I'm keeping the compressibility fixed, but changing the order of LABFM from 4th, 6th, 8th to 10th. And again, at 8th and 10th order, we encounter this compressibility related error limit, which is just an unavoidable consequence of comparing this compressible simulation with an incompressible analytical solution. But above that limit, we get, well, order of between 3 and 4, between 5 and 6, between 7 and 8, and between 9 and 10 convergence, which is very nice. So I've pointed out here that this is Eulerian, but although it's a rather slow simulation to conduct, I've also conducted this test with a Lagrangian plus particle shifting ALE scheme. And with that framework, where I have the particle positions updated with the third order Runge-Kutta scheme, along with the velocities and density logarithm, the convergence plots are unchanged. So the results are almost identical, and they would be identical when you look at them in the view of these plots, which is a nice feature because it shows that if we can have a good Lagrangian particle updating scheme, then we can get very accurate results with a Lagrangian mesh-free method. So Taylor-Green vortices are periodic, and it's really a comparatively easy problem. Boundaries, they present a more significant challenge, and that's because, so whilst partially filled stencils like this one on the left are okay, we can get away with up to the penultimate row of nodes at 4th order, and sort of the third from the edge row of nodes at 6th order. However, if we go all the way to the boundary, then even at 4th order, these stencils aren't okay. Actually, they're okay in terms of accuracy, but they're not okay in terms of stability. And the filtering technique that we have at the boundaries can't handle the high wave number noise that these stencils would introduce. So here's where we combine with finite differences. So on the boundaries, we use a strip of nodes in a sort of ordered regular distribution with 4th order one-sided finite difference stencils. And with these one-sided operators, that allows us to use a characteristic-based boundary formulation, which is particularly nice because then the numerical boundaries that we implement can be imposed in a way which is consistent with the physics of the problem. So we can use this for arbitrary geometries, but the caveat here is that we need to resolve the curvature of the geometries. So if we have a geometry with some very, very fine curves in it, then we need a very small resolution. Another nice benefit of these boundary conditions is that we don't have the additional computational and memory overheads of storing an extra set of ghost or mirror or dummy nodes or particles, as we often have to in SPH. So that this boundary framework is quite attractive because it doesn't increase the cost anymore by having these extra nodes. So on the bottom of this slide, I've got 2 examples. The first on the left is of a LAM ocene vortex passing out of the domain on the right with negligible distortion to the vorticity. So it's just a demonstration that this boundary framework combining LABFM plus finite differences allows for very nice, accurate, non-reflecting outflows. The second one is this video which shows flow past the cylinder, and again we can see the pressure field and the vorticity propagating out through the right hand, well, through the outflow with negligible distortion, and also, although it's not visible in this image, any pressure disturbances moving upstream are nicely propagated out of the non-reflecting inflow boundary condition. So briefly, I'll just show a small amount more validation. So we've compared the results with some experimental, some published experimental data. So this is flow past an impulsively started cylinder, and we match the experimental data quite well. So we have the center of the vortices in the same position. We get the stagnation point matching, and we also get the formation and position and size of these little secondary vortices matched quite nicely. On the right, we've got a comparison with the spectral element methods. So this is looking at the steady flow behind the cylinder. And when we look at the velocity profiles in these transects behind the cylinder, we get an extremely good match with published spectral element methods, which is just a nice little further sort of confidence booster that our code is doing the right thing. So far, I've not mentioned variable resolution, but that's not because LABFM is unable to handle it. Actually, it's because it's not an issue. So the only real requirement is that we remember to adjust the node spacing S and the stencil size H in tandem. Provided we do that, it works fine. So both these stencils, this uniform distribution and this sort of spatially varying distribution, both of those are fine. And on the right, I've got the convergence plots for the gradients on a non-uniform distribution, and you can see that we're getting second, fourth, sixth, eighth, and 10th order convergence all the way down to similar error levels, even with this non-uniform node distribution. This video at the bottom highlights the kind of node distributions that we can then generate. So this is flow past an ellipse, and I'll just go back to the start, and you can see that we've got really quite a significant range of resolutions. I think it's by a factor of about 80 over the domain between the smallest and the largest. And really, we don't have to do anything special to handle this change in resolution. We just have to make sure that we adjust the smoothing length H and the node spacing in tandem. I wanted to also mention here that the flow can handle the solver can handle quite challenging flows. So this is transonic flow past an ellipse. The color here shows the local Mach number, which is quite significantly above 1 in certain regions. And so we can capture the generation of shocks as vortices are shed off the ellipse. And I think at the second half of this video, it'll show that we can capture the acoustic noise generated. So yeah, this is showing the acoustic noise generated by this vortex shedding, and we see these little shocks propagating around the ellipse. I'll just skip to that again. So the method's capable of handling sort of incipient shocks without too much dissipation. So a final example that I wanted to show is a more complex geometry. This is a representative porous matrix, and discretization again is fairly trivial. So I've only just learned how to do videos like this, which is why you've got a lot of zooming in videos. But you can see again that we have our band of finite difference nodes around the porous, around the solid boundaries, and then we have a smoothly varying resolution, varying again by about 2 orders of magnitude between the smallest and the largest. So this video shows that the method can handle this type of flow for low Mach numbers. So this is a Mach number of about 0.15, a poor Reynolds number of just below 1,000, and and we can see the velocity field as more and more vortices are formed in the downstream section of the porous media. This video on the right shows a slightly more challenging case. So we've increased the pore Reynolds number to 2000 and increased the pore Mach number at the inflow of the porous media to 0.8. So we've got maximum local Mach numbers of about 2.5 in here. And again, the first part of the video shows the local Mach number. The second part will show the generation of shocks within the porous structure and the propagation of these as acoustic noise that the method can handle. Is quite robust in this regard. So this final demonstration case, I really included it because I wanted to show it's the kind of problem where we can be competitive with established mesh-based methods. Indeed, I think for problems like this, where we want to capture acoustics and we have to resolve the acoustic timescales, it's quite possible that a method like LABFM, because it's explicit, is actually going to be faster than a method like the spectral element method. It's also a case where we get the high accuracy of finite differences. So these simulations are all 6th order accurate in space, dropping to 4th order at the boundaries and 3rd order in time. So very high accurate simulations like we'd get with finite differences. But this is a problem that finite differences just couldn't handle because they're limited to relatively simple domains. And even if we use some immersed boundary methods in a finite difference scheme, they wouldn't be able to get such accurate boundary conditions. And the focusing of resolution where we want it again becomes challenging in immersed boundary methods with finite differences, because we're limited to grid stretching in a kind of Cartesian framework. So I've spent enough time showing what I think are the merits of LABFM. I want to spend a few minutes at the end talking about some of the problems which I think might arise as we develop LABFM further, but also as more and more high order mesh-free methods are developed. So the first challenge, I think, is related to incompressible flows. So here's my current implementation for incompressible flows. It uses a fractional step time integration scheme, and it's 6th order internally, dropping to 2nd order at the boundaries. But whilst the spatial discretization's accurate, I think it's let down by the boundary conditions and the integration schemes. So fractional step methods are limited to 1st order in time for global conservation of mass. And there are possibilities of other boundary methods, such as influence matrix techniques, which might guarantee conservation, but they'd come at a cost. So I think if we want to look at incompressible flows with these high order mesh-free methods, we need to think about what types of integration algorithms and both high order global and local boundary conditions we use. The next challenge is exact conservation. So in LABFM, I've sacrificed exact conservation in favor of high order consistency. And if I look at the global mass conservation error, so I think this is for flow past the periodic array of cylinders, it's still pretty good. It stays below one part in 10,000 for something like 500,000 time steps. But there are going to be certain applications where exact mass and momentum conservation are highly desirable. I'm not sure how this is going to be achieved. It might be that we need to move to flux-based, sort of almost mesh-free finite volume-based schemes, or it might be that we can incorporate these consistency matrices in some kind of global consistency matrix and regain some of the symmetries we've lost by sort of exploiting the sort of redundancies that we get when we use that that global matrix. I'm not sure how it's going to be done, but I think this is another challenge for these high order mesh-free methods, is that exact conservation is going to be one of the next desirable properties that we have to try and rebuild into them. I'm finally going to talk about some Lagrangian schemes. So in the Eulerian schemes, I've showed the cost of building and solving consistency matrices, and then building the weights is just a pre-processing cost. So it's relegated to the start of the simulation. In Lagrangian schemes, we have to do this every single time step. So I've experimented a little bit, putting LABFM in my incompressible SPH codes, and it works okay. The figure here is of a dam break. So the yellow shows where we've got fourth order LABFM. Orange is second order LABFM near the free surface, and then black is SPH on the free surface. So that's a nice approach, but it's not particularly accurate. And again, it's let down by the low order scheme that we have to update the particle positions. So ultimately, even if we're first order in time for velocity and fourth order in space for the discretization scheme, if we're advecting particles with a very low order scheme, that error ends up dominating. So maybe that we need some new Lagrangian specific time integration schemes. And actually my colleague Abazaid is doing some nice work on high order schemes for high order Lagrangian mesh-free methods. But these may involve several substeps, each with the nodes or particles at a new position, in which case we're then going to have to recalculate the weights at every substep. So I think the most significant aspect or challenge in making large scale, high order mesh-free schemes feasible is going to be the acceleration of solving the consistency correction matrices. So I mean, there's quite a bit of work on other high order mesh-free schemes going on. So there's high order corrected SPH. There's Riemann solver based schemes with Wiener reconstruction, and there's methods like the generalized moving least squares schemes, and they all require some form of polynomial interpolation, and that is going to require solving a linear system for every particle every time it or any of its neighbors moves. And so I think the key challenge is going to be finding ways of building and solving those systems as efficiently and fast as possible. And again, I don't know how this will be done, but I think this is probably going to be the biggest challenge for high order mesh-free methods in the coming years. So I'm about on time. Good. So to briefly conclude, LABFM allows us to generate arbitrarily high order difference operators. I've gone up to 12th order, but there's no reason I couldn't go higher, although the stencils get big and solving the linear systems gets expensive. So arbitrarily high order difference operators on an SPH-like node or particle distribution. And it can include spatially varying resolution and spatially varying accuracy. And the implementation we've got is pretty robust, so it can handle transonic flows, including shocks. The downside is it doesn't yield exact conservation, and it's not yet practical in a Lagrangian or ALE form. So it's effectively what we've done is we've sacrificed conservation, but we've also sacrificed efficiency in a Lagrangian framework for accuracy. If I had to sort of summarize LABFM, I'd say it performs very much like high order finite differences. And so far, anything that is implemented in finite differences that I've tried can be implemented in a LABFM style framework. But then the big advantage over finite differences is that is that we've got this geometric flexibility, so we can solve problems in geometries that unstructured mesh, that normally you'd have to use unstructured mesh methods or mesh-free methods for. So what's next? I mean, I've discussed this briefly. I think I've outlined a few challenges, but I just want to reiterate that I think acceleration is going to be the biggest obstacle if we want to retain what is seen as the key advantage of a mesh-free method, that it's easily constructed in a Lagrangian framework. Finally, I'd like to acknowledge my colleagues in the Manchester SPH group, in particular Abizaid and Steve, because this work really arose through a lot of discussions where we were sharing our mutual frustration at the discretization error and the accuracy of SPH. And without these discussions, particularly with Abizaid, I don't think this work would have happened. I think that's everything I wanted to say. So I'll stop there and I'll take questions now.
Thank you very much, Jack. Thanks for the great talk. There's a couple of questions in the Q&A, but also I'm able to allow people to speak. I have the power to do that. So if anybody would like to just verbalize a question, please put your virtual hand up and I can enable you to speak. Alternatively, you can use the Q&A, as three already have. We'll go to those in a second. I could just ask one question myself. So I see SPH as a very practical method. It's something that, you know, there's lots of practical uses for it, but inevitably you end up apologizing sometimes for the potential accuracy of the method for lots of the reasons that you've outlined in your talk today. And could you quantify what this does to the practicality of the method? So as an engineer just wanting to go away, use an SPH-like method to solve a problem with a complex free surface or complex sloshing behavior, what does this approach do to the general practicality of things?
It makes it a bit less practical, in short. I mean, the actual sort of the process of constructing high order weights or high order operators it's relatively straightforward. It can just be sort of stuck in a little module and just added onto an SPH code quite easily. But we're not at the stage where we've got things like handling free surfaces sort of stable with LABFM. So at present, if it was implemented in any kind of engineering code for any sloshing problem, we'd have to have sort of holistic approaches to trying to choose where we use SPH, where we use LABFM. If there are no free surfaces and you're happy to have a fixed geometry, then it's as simple as SPH. It doesn't, you know, you have to solve these consistency correction matrices. But if you're happy to just use an Eulerian framework, it's a very sort of straightforward method to implement and use.
Okay, thank you. Right, so let's move on to the Q&A. So a number came in from Xiaohu whilst you were talking, so I'll just give them in the order he asked them. So the first was, is there any way to measure particle distribution error separately?
So I mean, I suppose the sort of the point of a method like LABFM is that the error due to the particle distribution, I was going to say, doesn't exist. So in SPH, we've traditionally thought of there being two forms of error: a smoothing error and a discretization error. And the smoothing error is fundamentally due to the SPH interpolation procedure. The discretization error is due to our approximating SPH integrals with summations. When you look at things from the perspective that I've been looking at with LABFM, you kind of find that it's a bit more straightforward to stop separating the error out and just think of error. So at no point in the derivation do I think of anything in terms of a continuum. The error is just the error. So whatever error I showed in those graphs is the error in my polynomial interpolation plus the error from the residuals of calculating that polynomial interpolation. I hope that answers the question. I'm not sure if it does.
The second question from Jahu. With the same convergence order, have you compared the computational complexity of your LABFM methods versus FDMs, say comparing fourth order FDM with LABFM?
I haven't, but I can give an answer, which is, if you assume you're in an Eulerian framework, then all the costs of building and solving the consistency corrections, we can just call them pre-processing. So we'll discount them in the same way as we can discount the work that people did 100 years ago in calculating finite difference stencils. So the difference in cost is pretty much entirely related to the difference in the size of the stencil. So in fourth order finite differences, you've got, well, a stencil that has a total of 9 nodes, whereas in 2D that is, whereas for LABFM, you'd need a stencil that has about 20 nodes. Essentially, that's the difference between having a stencil that's a circle and a stencil that's just a cross. So you've got more nodes, so every loop where you calculate your derivatives, you've got more things to sum over. So the cost is going to be about twice what it is with finite differences, but it's going to scale the same, basically, because it's constructed in the same way. One thing I didn't talk about that we've been looking into is stencil optimization. So what we found is that we can actually sort of tactically reduce the size of the stencil, and that we can do that in such a way that we actually increase the resolving power of the method. So we keep the same order, but we can resolve a bigger spectrum, a broader spectrum of the broader part of the wave number spectrum. But we're also reducing the size of the stencil slightly, and that reduces the costs. So that's an approach that we're looking into, and I think that there's probably scope in there to head towards finite difference methods. But ultimately, finite difference methods get their efficiency partly from the fact that the symmetries enable you to get away with very few nodes in a stencil. We're never quite going to get there. I mean, the best we could get is if we had sort of unisolvent stencils. I've just seen Xiaohu's second question.
Yeah, it's a follow-on, isn't it, really?
That's an interesting question, actually. So
the question is that something like a compact scheme in finite difference method?
So one of the approaches that we've been looking at is, so I've just moved on to a slide that I didn't have time to show. And one approach that I've looked at is it's basically equivalent to a compact finite difference approach. So instead of becoming an explicit local method, it becomes an implicit global method where we solve a global matrix to get our derivatives. And that has potential to use slightly smaller stencils and significantly increase the resolving power. So on fairly simple cases, we've managed to go from resolving powers where we're accurate for, say, the first third of the spectrum to methods where we're accurate up to 2/3 of the spectrum. But this has quite a bit of work left to do to actually make it robust enough to use.
Okay, so the other question was more of a request, so I've put it to answer, and I'll let you have a look, Jack. So I think all the questions and answers are done. We're almost spot on time, which is great. I haven't seen any little virtual hands go up. So I think I can probably close this talk. And
Okay.
before we do, I'd like to thank you again, Jack, for giving the talk. It's very interesting. A very sort of new area, I think, probably for the SPH SIG and the sorts of works that have been shown in the SPH SIG before to go into and to have a look at.